Hi everyone, for today's lecture, we are moving into the last topic of our syllabus, which is topic 4.3, Networks and Decision Mathematics. So same as usual, I'll start with introducing to you everything that you will learn under this topic. Then after that, we come back to the learning outcome and start with today's content. Alright, so let's do a quick overview. Alright, as what I always mentioned previously, we know that the topics in Unit 3 and Unit 4, they are correlated to each other. For example, in 3.1, we have bivariate data, and 4.1, we learn about one of the special type of bivariate data, which is time series data. Then 3.2, we have growth and decay in sequence. Then 4.2, we are looking at how to apply growth and decay in sequence in a financial situation. So it's going to be the same thing as well for 4.3. So in topic 3.3, we learn about the basic of graph theory, which you know what is the element in a graph, what's the type of graph, then after that type of what Eulerian, Hamiltonian, so you know how to write an adjacency matrix and so on, right? Then we also talk about one of the simple application here, which is how to find the shortest path between two vertices, right? Okay, so in this topic, we are going to continue to look at different application in graph and networks as well. So there are a total of 4 different applications that you need to learn. So those are the 4 subtopics that we are going to learn under this topic lah. So the first one, which is what we are going to do today, which is called as the minimum spanning tree. So we are going to use 2 lessons to complete this, which is today's lesson and also Thursday lesson. All right, then after minimum spanning tree, we will talk about maximum flow. Then continue from there, we have project network. Okay, so how are we going to show our project planning on the network then to find the critical path and also the completion time of your project? All right, then lastly, we have allocation problem. So sometimes it's also called as assignment problem. So it depends on how you want to say that, but the idea is the same. All right, so you will realize that in everything that you are going to learn, there's going to be something which is called as algorithm. So this is the words here. So what is that meant by algorithm is a precisely and something that is very systematically defined procedure. So what you need to do is there's some kind of routine that you will need to follow so that after you finish off the routine or the procedure, then you will be able to get what you want to achieve out of this so-called experiment. All right. So each of these different application, they have its own algorithm. So that's why what is very important when you move forward, right, is that you will need to understand what is the different situation and what is the problem that you are solving based on the different application here. So when you have all these different questions in your exam, you'll be able to understand them, then also to differentiate the situation given. All right, so yeah, because when you are having your exams, right, then the question wouldn't tell you like which method that you should use. So it's the same thing like when you learn AP, GP, you need to differentiate them, right, by looking at their characteristic. So it's the same thing here. You need to understand what are the different problems that you are solving for each of these application, so that in the exams itself, you will be able to solve it by using the right algorithm. All right, so let's start with today's lesson, which will talk about minimum spanning tree. All right, so there are 3 things that you need to know, but basically the main point of it is to learn how to find the minimum spanning tree lah, right? Okay, so the first one is you need to know what is that meant by trees and also spanning tree. All right, so these are the definition part. Then after that, we are moving onwards to algorithm. So you are going to learn 2 different algorithms to solve or to find out what is the minimum spanning tree in a weighted connected graph. All right, then last but not least, why you are learning this is because you want to use minimum spanning tree to help you to solve problems, right? All right, so basically they are referring to the same thing lah, no matter you are talking about the second one or the third one. So the idea is you know how to find, then after that you will be able to apply it already. Okay, so let's look at the definition. All right, the first thing, what a tree is. So a tree is a connected graph. All right, so I hope that you still remember what a connected graph is. So it's a graph without any isolated vertex, and you cannot have parts of the graph which are disconnected from each other. All right, so for example, you can see that every vertices here, they are connected to each other. So they doesn't need to be adjacent, but they need to be connected. All right, so a tree is a connected graph with no cycle. So you can see inside this graph that you don't have something that is like this. Yeah, so if let's say I try to draw one, then you can realize that this is a cycle. Okay, so that's why it is not a tree anymore, lor, right? So and then you can realize that it's like somehow like a shape of tree, like you can try to remember like that. But the real definition of a tree is that they must be connected, and then there's no cycle in a tree. All right, so we are going to do this very quick. I think is quite simple as well. Okay, so for question A, so do you think this is a tree? So you can see you have four vertices A, B, C, D here, but then you realize that there's a cycle, right? So that's why A, it is not a tree. So reason being is there is a cycle. Okay, so it doesn't need to be like the whole graph is a cycle, so which means like what I have drawn just now. So you can realize that it's not the whole graph is a cycle, it's only one part of it is a cycle, but then you cannot contain any cycle in your graph lah. Okay, then after that, part B. So is this a tree? So you can realize that A, C, E, F, they are all connected to each other, right? And then there's no cycle, so that's why yes, it is a tree. Okay, C. So you realize there's no cycle inside this graph, but you realize that CD and also FH, they are disconnected from each other. So that's why the answer is no. So reason being is it is not a connected graph. Oops, it is not connected. Right. All right, so that's the idea. So I hope that is quite easy. Then next part, we are going to look at what a spanning tree is. So a spanning tree is a subgraph of a connected graph that connects all the vertices. All right, so let me try to explain further by using this simple diagram here. So you can see that this is a graph, right? Okay, so which means that if let's say I try to draw something like this, okay, so please look at the vertices, the edges that I try to draw with the purple color here. Okay, so if I draw something like this, then this is called a tree because you can see that they are connected and there is no cycle. Am I right? So this is called as a tree. So when we talk about spanning tree, you will need to have further one more condition, which is they must connected all vertices. So which means that this is not a spanning tree yet because these vertices and these vertices is not involved. So that's why if I want to make this a spanning tree, then I will need to add on this one and then this one. So this is a spanning tree because you involve every of the vertices and also they are no cycle together. All right, so as you can see here, so the one with dotted line is actually a spanning tree, so which means this one. Okay, so you can see that it's a subgraph of this connected graph. Subgraph meaning that you cannot add in any other edges lah, right? So you are going to use the exactly what is given here. So it's a subgraph that connect to all the vertices here. All right, so now we'll be looking at one simple question here. So the following graph here outlines the current water system between the garden beds. So a plumber have noticed that water is being wasted as too many pipes are being used to connect the different garden beds. So question one is to draw a spanning tree for this graph. All right, so looking at this situation, so the idea here is that you imagine, right? What happened here is all the vertices here, they represent the different garden beds. Okay, so if you want to water the plants in the garden here, then which means that you need to only have one pipe that connected to it. So for example, to reach B, right, it's either I use this edge to connect to B or I use this edge to connect to B. So I doesn't really need both. So if let's say A or B is connected to A already, then which means B doesn't need to connect it to D anymore. So that's the idea. So you can have different answer than mine, but the idea is to make sure that you do not have any cycle and then you involve every vertices in this graph. All right. So I'm just going to start with if let's say I'm trying to use this. Okay, so another branches up, so maybe here. All right, so FG. So since G is also connected, so I doesn't need to go back, right? If I go back, then I'll form a cycle here already. Then after that, maybe H here. So here, okay, and then here, either you want to draw here or you want to draw here also can. So this is like one of the spanning tree of this graph. So again, you doesn't need to have the exact same picture as mine. So what is important is to make sure that you involve all the vertices and you cannot have any cycle inside. All right, so I'm going to draw my spanning tree here. So the other alternative is you can try to draw it like this. So you can try to show all your vertices first. So yeah, like mine, then I'm going to do this. Okay, then I have E and then F, okay, and then H and G. Okay, so after you draw this, then you choose yourself. So you can see everything is here already, right? So if let's say you want to pick here, okay, and then continue. So you cannot leave anything isolated, right? So that's why that you need to connect to them. So if let's say you don't like F and H, they connect to each other, then you can connect G and H also. So it's either you want to do here, you want to do here, or you want to do here. Okay, so the idea is make sure there's no isolated vertex. That's it. All right, so I'm just going to draw exactly the same thing like what I have done previously. Okay, so this is my tree here. So make sure include all the vertices and then you do not have any cycle. All right, so according to the spanning tree, which edges has been removed? So in this case, I have removed AB, I have removed AE, I have removed EG, and I have removed GH. Okay, so in this case, for me to water the plants in all the garden beds, actually these are the necessary ages that I need. I doesn't really need the 4 here because water can actually be transferred to every places here already. All right, so that's the idea. So I hope that you get an idea on what a spanning tree is. And now we are going to look at what is that meant by minimum spanning tree. Alright, so we're going to understand what a minimum spanning tree is by using this situation here. So suppose that the network below shows the root exists between 9 farms, so A, B, C, D, F, G, H, I. So the weights here indicate the distance to reach each farm here. So the water authority wishes to connect all the farm to the main water supply by laying water pipes alongside the existing road here. Alright, so by looking at this network, of course, if let's say I do not want to do any planning, right, then what I can do is, of course, I can just lie water pipes alongside all the roads here. But you can imagine that that's not going to be very efficient and that's not going to be very cost effective as well. Because eventually, if let's say you are going to lay water pipes on every of these edge, right, then it's going to give you the maximum cost or it's going to give you the maximum distance of the water pipe that you actually need, right? So that's why by looking at this situation, then what we try to do is, okay, for example, if let's say, let me try to connect all these together first. Okay, so these are the existing root that I'm having here, right? So I would realize that we can try to remove some of the unnecessary roots. For example, if let's say I realize that, okay, this is the longest one, since I can connect to B and E already, so I doesn't need this H. I can do that, right? So since B and A is connected as well, so I can remove this one. So I can remove this, I can remove this, I can remove this, and I can remove this, and I can remove this, and yeah, that's the last one. Then I realized that this route can actually allows me to actually go through every places, and I do not have any unnecessary connection. So which means that the water are able to transfer to every location here by using this spanning tree. So in this case, what we are trying to do here is that we need a system that includes all the farm, which has no unnecessary connection. So for what I have done just now, so I'm just like I'm just like removing the line randomly lah, okay? But of course, what we are trying to do here is to find the shortest one. So what we need here is actually called as the minimum spanning tree. All right, so what is a minimum spanning tree? So for a given connected weighted graph, the minimum spanning tree is the spanning tree with the minimum total weights. So which means that if let's say we are talking about the distance, then which means that of course you want to find the spanning tree with the minimum distance that you need to lay the water pipes, so that the cost that you need will be minimum as well, right? So I hope that in this case, right, you will be able to differentiate the thing that we are doing now versus the shortest route that we discussed in our topic 3.3. Okay, so let me try to remove this. If you can recall, right, in shortest road, we talk about the situation where you have one starting point and maybe you have one ending point. So when we are talking about a shortest road, we are finding the shortest path that allows you to travel from A to I. So the idea for shortest route is that, for example, I'm working here and I need to go back to my home at I. So what I need to do is, okay, maybe I realize that this is the shortest way that I can take. So this is my shortest route to go back to my home, right? So you realize that to go back to my home, I doesn't really need to go through all the farm. So as long as I find the shortest route for me to reach my home, and that's going to be my shortest route, I doesn't need to include all the variances in the situation. But then when we try to talk about minimum spanning tree, you can see that the application is different. So the thing that we are looking here is that, for example, you want to, so like what we say here, so you want to find out what is the, how you can lay the water pipes so that the water supply can actually provide it to every farm here. So that's why the thing that we need here is a minimum spanning tree, is not a shorter route. All right, so I hope that you can see the difference here. So for what we have done just now, right, is that I try to include every of these edges, then I try to remove it one by one. So you can imagine that's not going to be very effective, especially if you are having a very large graph. Then you'll realize that you will need to try and error or doing inspection, then it's going to be like quite challenging. So that's why what we try to do is we will be learning two algorithms so that it can help us to find out the minimum spanning tree in a network. So there are two that we need to learn. So the first one is called as the Prim's algorithm. All right, so for Prim's algorithm, we are going to look at two different ways for us to do this. So the first one is by looking it in a network. So which means that you are having your network diagram like what we have just now in our example. So we can use Prim's algorithm to find out what's the minimum spanning tree here. Then the second one, we are going to apply it in a distance table as well. So this is a thing that we are going to look at it on Thursday lesson. All right, so for today, we are going to look at network diagram only. After that, the second one is called as the Kruskal algorithm. So no matter which one that you are using, you will be getting the exactly same answer. So that's why you can just, you will learn to, then after that, it's based on your preference that which one you prefer, because no matter which one you are using, at the end, the solution will just look the same. So we'll start with the first one, Prim's algorithm. So you can remember this algorithm as the method of choosing vertices. So the algorithm looks like this. So choose any vertex to start, then slowly build up your spanning tree by connecting to the neighbor with the minimum weights until all the vertices are included, and make sure that no cycle is introduced. All right. So you can see that I put in different steps here so that it's easier for you when you try to do your revision in future. But then everything that we are doing is just a repeating process. It's just like a very systematic procedure. All right, so let me try to just change my pen here. So if you can, then you can try to use your highlighter, then I guess that will be easier. All right, so step one, choose any vertex within the network as the starting point. All right, so we are just going to do the easiest one first. So I'll start from A. All right, so among the adjacent vertices, so remember Prim's algorithm, the method of choosing vertices. So look at the vertices that is adjacent to the one that you choose, then find the vertex that give you the minimum weights. So you can see that B and C are both adjacent to A. Which one give you the minimum weight? Of course, 11 is shorter than 12, right? So that's why I'm going to pick B. So when I pick B, then which means that I'm going to choose this H. All right, then moving onwards for step 3, let's try to draw the one that we have chosen in step 3 first. Okay, so repeating the same thing, you are going to look at the adjacent vertices, but the only difference here is that now you have vertices A and B already. So you are not only looking at those adjacent to A, but you also look at everything that is adjacent to B. So that's why you are having a choice of C and E now, right? So because these are the two that is adjacent to A or B. So that's why which one give you the shortest one? So you can see that you have 12 from A to C, 7 from B to C, or 22 from B to E. So obviously the one that is shortest is going to be 7. So that's why this will be the third vertices that we will be choosing. Okay, moving forward, same thing. These two we already chose. Okay, so now next one. Now you will be having three vertices, so A, B, and C. So again, choose the vertices that give you the minimum weight. So now you realize that you have BE, CD, or CF, and AC. But then you realize that when we talk about spanning tree, we are not going to introduce any cycle to your tree. Am I right? So that's why you are not going to draw anything on AC already, because that's going to form a cycle. On the other hand, you can try to think about if we talk about laying water pipes, right? If the water can already reach A, B, C, then why you want to add in one more edges here? So that's the idea that you should have in your mind when you try to solve this question. Okay, so now we are having BE, CD, and also CF. So that's why the shortest one definitely is going to be CD. Okay, so same thing, moving onward. So these are the four vertices that we have chose. Okay, so now you will be having four vertices to look at. So A, B, C, and also D. So the one for the neighbors for these four vertices will be BE, DE, DF, or CF. So from here, the shortest one that you are having is, yeah, DF. Sorry, I missed to say the DG just now, okay? So BE, DE, DG, DF, and also CF. So that's why the shortest one will be choosing the vertices of F. Okay, so moving forward, so same thing, we're going to do the same thing here. Alright, so now you have a total of 5 vertices to look at. So A, B, C, D, and F. So the same thing, the one adjacent B, E, D, E, D, G, F, G, right? So those are the ones. So which one is the shortest? So now you realize that there are two shortest ones. Either you choose DE or you choose FG. So in this case, which one to choose? So no worries about that. You can pick anything that is, I mean, if let's say you have the vertices that give you the same weight, then just choose either one. Because you can imagine that when you repeat the routine, right, you are, I mean, no matter you choose this one first or this one first, later you are going to choose the other one. You get what I mean? If you are choosing your DE now, then later you'll be choosing your FG. If you are choosing your FG now, then later you'll be choosing your DE. So that's why it doesn't matter. So in this case, maybe I try to choose my FG first. Alright, so that's the thing. Okay, so now same thing for last one. Okay, so let me try to draw everything that we have found just now. Alright, so yeah, I'm not splitting this into different steps already because you can realize that it's keep on the same thing going on, right? So repeat the same step until all the vertices in the graph are included. Alright, because we talk about spanning tree, you must make sure that you can reach every vertices here. So that's why in this case, we still left with E, F, H. Okay, so now the one that is adjacent, B, E, D, E, and then G, E, or DG. So same thing, you realize that you are not going to put any edges on DG because that's going to form a cycle and you already reaches DG. So that's why there's no point that you want to add in them. So that's why in this case, then it will be DE. Okay, so moving forward, then you realize that the next one, so BE, you are not going to draw it anymore because that will give you a cycle as well. So EG also, so that's why we are just going to continue. So EH, GE no more, GH or GI. So the shortest one is GI. Okay, then moving forward, the same thing, which one give you the shortest one? So of course, GH. Alright, so this will be our answer here, and this is going to be our minimum spanning tree. So always check at the end that all vertices are included. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So they are correct. So all vertices are included and there's no cycle, right? So that's right. So the number of edges involved in the spanning tree will always exactly one less than the number of vertices. Because you can imagine when we talk about a tree, so you are not going to have any repeating edges. So that's why you can imagine that if let's say you are having like a connected graph with 9 vertices, then obviously you are going to have 8 edges. So for example, I just give you a simple example. If let's say I have point here, what is the minimum edges that I need so that they are connected? So obviously 1, not enough, right? Because you have isolated. 2, not enough, you still have isolated. So when you try to draw one more, do you still need extra? No, right? Because they are connected already. So the same thing, if let's say I try to draw here also can. So I need minimum 3 edges so that I can connect 4 vertices. So it's the same thing here. If let's say I have 9 vertices, so which means at the end I will have 8 edges. So 1, 2, 3, 4, 5, 6, 7, 8. So that's why this is correct. Okay, so this is the answer for my minimum spanning tree. And now we are going to find what is the minimum length of road that we need. So that's why in this case, the minimum length will be equal to, so minimum length. Okay, so equal to 11 plus 7 plus 16 plus 7 plus 8 plus 8 plus 9 plus 7. Okay, so remember 8 number, 1, 2, 4, 6, 8. So that's why that's correct. So just key in everything in your calculator. Then from there, you'll be able to get your answer, which is equal to 73. 18, yeah, 73. All right, so this is KM, I think. Okay, so this is the way how you solve it. Then you can try, if you are using this algorithm, right, then obviously you will get the minimum answer already. So you realize that no matter which one that you are exchanging it with, right, so definitely that's going to give you a bigger answer. So you can imagine lah, if let's say here you are choosing it to 12, then which means you have 1 extra, right? So if you don't want to pass through this and you take 22, definitely that's going to be longer. If you choose the other one, that's going to be the same thing as well. So that's why that's the case. Okay, so we are going to repeat this method as well, but then we try to use the other vertices as our starting point and see whether we can get the same answer or not. Okay, so let's try it out, and also it's like the revision for the steps that we have done just now. Okay, if let's say I start with D, okay, let's see is there any difference. So if I start from D, then my neighbor will be C, E, G, and also F. So the shortest one is F. Okay, so now I have DF. So I have, so there's no neighbor added, but I can obviously go from FG as well. So here, 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 here. So that's why it's either I choose 8 here or 8 here. Okay, but it doesn't matter because at the end I know that after I choose this, then I have 22, 10, 10 is going to be smaller than 8 as well. So next one I'm going to choose here. So now I'm going to look at E, D, F, and G. So 16, 21, 22, 10, 10, and 9, 7. So 7 is the shortest one. Okay, so moving forward, now we have I. So the other shortest one will be the 9 here, right? So now each is connected. So that's why even though 10 is the shortest one for the neighbor, but then you realize that no matter which one that you are taking, you are going to form a cycle. And also you already reach E, H, and I. That's unnecessary. That's meaningless if you want to add on the edges here. After that, continue. So we have the choices here. So 16, 21, 22. So this is the shortest. Okay, so now we have C here. So obviously 22 you are not going to choose. So 7 is the shortest one. Okay, then 12 and 11. So that's why 11. So you should realize that the shape of the spanning tree that you'll be having is totally the same. All right, so the answer is the same. Then after that, the same thing. Let's try this out. If let's say I'm using I. Okay, so the adjacent one, 10, 7. So 7 shortest. Okay, then I have G here, 8, 9, 10, 10, 10, 12. So shortest 8. Okay, so now I include F. So the shortest obviously 7. Okay, then after that 10, 9, 10, 8, 16, 21, 22. So the shortest one 8. Oops, sorry. Let me try to just make it a bit nicer. Okay, 8. All right, then moving forward, 9, 10, 10, 22, 16, 21. So shortest 9. All All right, then moving forward. So now you have everything included here already. So same thing, we are going to look at the left-hand side, then obviously 16, 7, and then 21. So you realize that the shape is the same. So you will realize that if let's say you use different starting point, the vertices that you are going to choose will be in different sequence. Like what happened just now, like if let's say I start from I, then I might be choosing like G first and then F first, then the back only I got H, right? So that's the only difference that you'll be having. You are going to get the vertices in different order, but at the end, your minimum spanning tree should be the same and the minimum length that you find should be the same as well. Alright, so I hope that you get the first idea, which is to use Prim's algorithm, the method of choosing the vertices that give you the minimum weight. Alright, so now let's look at the second one, which will be using the Kruskal algorithm. Sorry, I'll try to change this in your handout. Alright, so the second method here, Kruskal algorithm, you can remember it as the method of choosing the edges. Alright, so the first one we talk about prims, so that is choosing the vertices. So for this one, we talk about choosing the edges. So we are going to start with the edge with the minimum weight, then after that continue to choose another edge with the minimum weight. So we are going to repeat this routine until all the vertices are included and make sure that you are not creating any cycle in your spanning tree as well. So that's why in this situation, we are using the exact same question that we have in the previous one. So I'm going to show you that no matter which method that you are using, at the end, you will be getting the same answer. Alright, so remember the method of choosing edges, Kruskal's algorithm. So the first one, just look at the network here, which one give you the shortest one. So remember, if there is more than one edge with the lowest value, just choose either. So in this case, you have 1, 2, 3, there are 3, 7. So you just choose either that you like. So for example, if let's say I choose here. Alright, so for the next one, I'm going to continue with the same thing. So step 2, I'm going to choose the next edge with the minimum weight. So you are not going to care whether it's connected to the previous vertices or not, as long as it's the minimum that you are having in your network. So that's why there are 2, 7 left, right? So you just choose either one. So for example, I choose GI. Okay, so moving forward, so I think this one is very easy. So that's why I'm just putting like 3 steps. Okay, so I have 7 and then I choose this 7 just now. So the same thing, the next one with the minimum will be the 7 here as well. So step 4, just repeat the same step until all the vertices in the graph are included. Okay, so that's why just now I already draw 7 and then I'm going to continue another 7. So same thing, 7. So next one, which one is the shortest one? So I'm going to have 8 here maybe. Okay, then can I choose this 8? Can, right? Because you realize that even I try to connect here, there's no cycle yet. So that's why FG, the 8 here. So which one is the shortest one? Is the 9, right? So that's why 9. Okay, then repeat, I have 3, 10. But then this 3, 10, no matter which one that I'm choosing, I'm going to create a cycle to the graph. So that's why I'm not going to choose any 10 here. And also they are already connected. Okay, so that's why the next value will be 11, the shortest one. So that's why 11 here. Okay, so the next one will be 12. But then 12, I'm going to create a cycle as well. And A, B, C, they are already connected. So that's why you doesn't need that. So now you're only left with this part of the graph and this part of the graph didn't connect, right? But then you can try to use the same idea as well. So for remaining one, 10, 10, 10, creating cycle, 12 also creating cycle. So 3 that you left will be 12 here, creating cycle as well. So 16, 21, 22, which one is the shortest? 16. So now you realize that you have all the vertices are included and then no cycle. So that's why that's going to be your end. So you realize that this shape is exactly the same with the answer that we have in the previous question. Alright, so this is the case for Kruskal, and the length of the root, then the same thing. Just do it as routine. So just write down our minimum length here. Okay, so the length of the root will be equal to 11 plus 7 plus 16 plus 8 plus 7 plus 8 plus 9 and plus 7. Okay, so at the end, you should be able to get the same answer as well. So let me just try it out. 7, 8, 16. Alright, so 73. So that's why this answer is the same. Okay, so you should realize that if let's say you are going to compare between these two algorithms, right? So obviously I think Kruskal is easier. So I'm just putting a notes here. So you observe that no matter which algorithm that you are using, right? At the end, you are going to get the exactly same solution. So if you were to ask me which one is easier, if let's say your graph is having lesser edges, so for example, in all the situations that we are having in our course, normally the graph wouldn't be very dense. So in that case, right, for a graph with lesser edges, actually Kruskal is easier. Because what you need to do is just to find out the shortest, then you highlight, find out the shortest, then you highlight, then just make sure that there's no cycle included, right? So however, in a dense graph, so which means that you can imagine if let's say I'm having a graph with like 100 edges, so it's like a very huge graph. You can imagine that if I'm having like 500 edges lah, so you realize that it will be very hard to do Kruskal because you might want to compare between like 500 edges and to find out the shortest one. So that's why for a dense graph, meaning that a graph with a lot of edges, then prims will be easier because you can start from anywhere that you want. Because in Prims, we talk about choosing the vertices, right? So as long as you have one starting vertices, then you can slowly extend your minimum spanning tree by looking at the adjacent vertices, then you slowly extend it. All right, so that's why in a dense graph, Prims will be much more easier. But normally in our course, you can imagine, I mean, they won't give you like a network that requires you to find out the minimum spanning tree for like 500 edges. So that's why it's just based on your preference, like which one you prefer. Then after that, you just apply it, right? Okay, because you can realize, right, no matter I'm using Kruskal here or I'm using Prim's algorithm, actually at the end, right, the method will just look the same. So that's why if let's say I'm not the one that applying that, by looking at your solution, I wouldn't be able to differentiate that which algorithm that you are using. So that's why they are totally fine, because at the end, the answer, the solution, and the method that you are showing are just the same. All right. Okay, so now we'll be looking to last question together. So it's like a quick exercise for you before you move on to your individual exercise. All right, so let's look at question 1. All right, the map below outlines certain buildings in a university. So the vertices represent the building and the edges here represent the existing path. Okay, so the weight represent the distance. So the maintenance team want to cover some of the path so that the students stay dry when it is raining. So for the maintenance team to keep the cost down, so they wish to find the spanning tree with the minimum distance. Okay, so it's the same thing you can imagine as if, I mean, if I were to save the cost, at the same time I want to be able to reach to every vertices here, then what I need is a minimum spanning tree. Okay, so now let's try to do it by using Prim's algorithm first, then after that Kruskal algorithm. I'm going to explain one by one again for the last time here. Then after that, for a second question, I'm just going to show you the working. Then after that, you can try to check yourself. All right, so you can start with anywhere that you want. So if let's say I choose to start from C maybe, okay, then after that I'm going to choose, so my neighbor 1 2 3 4 5 6, so the shortest one is 190. Okay, so now I have two more neighbor here, 1 2 3 3 more neighbor here, so the shortest one I have 180. Okay, then after that plus in S3, then the shortest one I have, that is the neighbor for C, S1 and S3 will be 190. Okay, now after that 200 going to form a cycle, so I'm not going to pick here. So I'm going to go back here, 400, 270, 200, 390 and 350. So that's why 200 and 300 here. Okay, so definitely you can see that the neighbor here is going to give you the shortest one now, so 180. After that, this one is still more than that, so 190. Okay, so yeah, this is going to form you a cycle, so that's why you're not going to look at this anymore. So 400, 350, 390, 400 and 270, so that's why 270 shortest. Okay, then the next one is 180. Okay, so every part here is covered already, all the vertices here already included, so you're not going to look at this one. So these are the two left. So 390, 350, 400, so that's why shortest here. After that, the next one, 180. Okay, so we leave our answer for the last part. So now we move on for Kruskal. So same thing, remember, is a method of choosing the choosing the edges, right? So that's why straight away look at everything. So you realize that for this one it's a little bit tricky already because there are quite a lot of number if you compare to the previous one. So that's why between all the number then pick the shortest one. So we have 180 last. So yeah, you can highlight all 180, 180, 180. Next one will be 190. So 190, then 190, 190. So always make sure that when you're highlighting, there's no cycle formula because sometimes Kruskal you might do it like quite fast. So at the end, you realize that you miss out something. So for example, you see 180, I miss out just now. Okay, so now continue. So yeah, there's nothing start with 1 already. The next one will be 200. Okay, so do I have 110? So 200, no, 210, no, 220 here, but it's going to form us a cycle. So that's why the next one that shortest is going to be 270 already because anything under that is more than 300. Okay, then 350, 350, and yeah, that's the two shortest one. But then you realize that this is going to give you a cycle. So here, no more cycle, so that's why this is the one. Okay, so you realize that at the end of the day, your spending tree will look exactly the same no matter which method that you are using because you can see that the outcome just look exactly the same. So if let's say I'm the one that marking, I wouldn't be differentiate that which one that you are using now. Okay. All right. So the minimum distance. So let add up together. So yeah, you might want to follow some kind of sequence that you don't miss out anything, right? Okay, so if let's say I am going to start with C again, so I'm going to go this way, go this way, go this way, and go this way. Okay, so depends on your own preference. So 350 plus 180, go back to C, 190, go down 180, then 190. So go back to C, go to N1, N3, N2, go back to C, go to E1, and then E2. Okay, so one way to check it out is also to calculate the number of vertices that you're having. So remember, like what I said, the number of edges involved will be exactly one less than your number of vertices. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you should have 10 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's why that's correct. Okay, so add them up together, you should be able to have 2110, and this is in meters. All right, so this is the shortest way, and I mean it's going to be the cheapest way so that you can try to just put in the cover or the path so that the students will be able to reach all the destination although it's raining lah. All right, so now let's look at question 2. All right, so yeah, there's one thing that I want to mention here. I realized that there's going to be this thing happen when we try to do this chapter. Reason being is, I already tell you that this is minimum spending tree, so that's why without needing to think about anything, then you are just going to apply Prim or Kruskal in this case. Okay, but what I want you to do when you try to do your exercise or when you try to watch this video, right? Try to really go through the question and understand why you are doing minimum spending trade. Because at the end of the day, like what I say, you need to differentiate yourself like, so for example, if I were to give you this question without telling you that it's minimum spending trade, do you able to understand the situation and to apply the right thing? So which means that you are not going to find like shortest path or you are not going to do maximum flow. You get what I mean, right? So that's why you will need to read the question and to understand. So when you are trying to understand the situation that you are applying minimum spending tree, next time when you're looking at the question again, you will be able to understand and apply the right thing. All right. Okay, question 2. Eugene wishes to connect electricity to 8 sites in a park. So these are the 8 sites, 1, 2, 3, 4, 5, 6, 7, 8. So from S1 until S8. So the weighted graph on the right indicates the direct distance from each site and the location of the electricity source. So this is the electricity source. So find the least amount of electric cable that Eugene need to use to connect the electricity to all the 8 sites. Okay, so same thing also you can imagine. So you will need to involve your P. Then after that, how your electricity cable is connected, it will be depending on which one give you the shortest distance between all the side here. So that's why what you need is you need to involve everything, right? Involve all the vertices and you do not want to have any unnecessary ages. So that's why you are using minimum spanning tree. Okay, so in this case, I'm not going to explain the algorithm anymore because I believe that you should be quite familiar with this. So just try it out, and I'm just going to show you the, my sequence, and after that, you try to compare yourself. Okay. Alright, so after you get the answer, if let's say you find this shape a little bit awkward, then you can always try to check now. So S1, S2, S3, S4, S5, 6, 7, 8, and P, they are all connected. So that's why it's correct. Okay, number of edges 1, 2, 3, 4, 5, 6, 7, 8. So that's why 8 edges with 9 braces. So that's why this is correct. Alright, so let's try to find out our minimum length for the electric cable that needed. So let's do the left hand side first. 7, 8, 9, 10. Right hand side 11, 8, 10, and also 9. Alright, so yeah, you can try to use this chance to practice for your, what is that called, your manual calculation as well. So 9, 15, 15, 9, 24, 34, 45, 53, 53 plus 19, that's going to be 72. Okay, so 72 meters. Alright, so that's this question. I hope that is actually quite clear enough. So again, I hope that when you are trying to do the question, so you are not straight away go for the network diagram, then you try to solve it, especially for the for the last few question. So try to really go through the question itself and try to have a better understanding on why you are using minimum spanning tree. Alright, so that's basically for this part. And for Thursday, we are going to talk about how to use Prim's algorithm in a distance table. Alright, thank you.